Hey folks, in this video my colleague Dr. Neil Spinner will be giving a crash course or video tutorial on our AfterMath Electrochemical Studio software. If you have purchased a potentiostat from Pine Research Instrumentation, you may already have this software on your computer. But if not, you can download it for free off of our website. Link is in the description below. This video is broken up into several sections. We will go through almost every topic in AfterMath, from how to create an experiment to importing and exporting data, using tools, using transformations, etc. A full list of all the topics is in the description below with timestamps to help you navigate the topic that you are interested in. Lastly, before we begin, please don't forget to like, comment, and subscribe.
The first screen you will see when opening AfterMath is the home screen, which provides a few quick options. These include links to common experiments like cyclic voltammetry, open circuit potential, or electrochemical impedance spectroscopy, a link to create a new blank plot, links to recently opened archives, and also links to the Pine Research website and other resources. There are many customizable features that allow you to tailor your user experience in AfterMath to your personal preferences. For example, you can adjust the default units that it will appear in new plots and data. You can change the color scheme and also adjust the plotting conventions for X and Y data. For example, by default, AfterMath displays data according to what is commonly called the European or IUPAC, or UPAC for short, convention, where positive current represents oxidation and negative current represents reduction. However, these preferences can be inverted for potential, current, or both, which would adjust the data plotting to be more in line with what is commonly called the Texas convention. Moving on to the top menus and buttons, we see standard kinds of options that are available in most Windows-based programs. In the Edit menu, for example, we see typical options like Cut, Copy, Paste, and Delete. In the File menu, similarly, we see normal options like New, Open, Save, Save As, and Close. Additionally, an option exists to import external data. The Experiments menu shows all the electrochemistry experiments available to be performed. The list of experiments is grouped by the type of method, and in some cases, there are sub-menus with various techniques related to certain kinds of experiments, like corrosion or impedance spectroscopy. Note that the specific experiments visible may be limited to the permissions files that are present on the computer running AfterMath, and only certain potentiostats can run certain experiments. For example, only AC-capable instruments can perform impedance spectroscopy experiments, and only bi-potentiostats can perform dual electrode methods. The Analysis/Tools menu includes a variety of options that may differ depending on the version of AfterMath being used and the set of permissions files present as well. These may include EIS analysis tools like circuit fitting and transmission line fitting, as well as electrochemical simulation modules. Some of these tools may only be added to specific types of data. For example, circuit fitting modules may only be applied to EIS data. Organization within AfterMath is made convenient using a variety of different options, such as notes and folders. Much like your standard PC Windows-based file explorer, data files can be grouped together in separate folders, and notes can be added to document experimental details, as one might do with a laboratory notebook. A layout is an organizational sheet where multiple items can be displayed for viewing or printing purposes. Right-clicking on the layout and selecting Properties allows you to adjust the format of the layout. Plots, notes, and other items in AfterMath can be dragged and dropped into available panels to populate the layout. It may sometimes be necessary to format a plot separately before adding it to a layout for optimal viewing of the data, axes, legend, and other plot features. Blank plots can also be created and scientific data imported from secondary programs. When importing data, AfterMath will prompt the user to select the units, if any, of the X and Y data streams. Scientific SI unit conventions are programmed and maintained in AfterMath so that unit transformations can be performed as desired. If you wished to change the current axis on a cyclic voltammogram to current density by dividing the y-axis data by surface area, you could simply right-click the trace, then choose Apply Transform and Basic Math Operations. Choose Division, perform operation on y data only, which is the current axis, and choose Area from the Operand Unit Selection dropdown. Type in the area of the electrode in the operand value box and click OK. The trace is now transformed and relabeled as current density. Another example might be if a power curve is desired to be generated from a linear sweep voltammogram, which in this context might otherwise be known as a polarization curve. Perform a basic math operation once again on the trace, and this time select XY product. Uncheck Replace Original Trace so that it will add the power curve without removing the original trace. Then click OK. The newly created trace has units of milliwatts, which is the product of volts and milliamps. Also, since this unit does not already exist on the plot, a secondary y-axis with units of milliwatts is automatically generated to accommodate the new power curve trace. Navigating plots can be done in several different ways, including zooming in and out, panning, and selecting various parts of the plotted data. The default plot selector arrow is the leftmost icon that selects entire traces. Holding down either the Shift key or the Control key on the keyboard allows you to select multiple traces at once. The other selector arrows allow you to select individual points, either by clicking one at a time or dragging a box around the desired points. And the last selector arrow allows you to select segments. A trace may consist of one or more segments. So when a trace contains only one segment, there will be no difference between using the trace selector and segment selector. However, when there is more than one segment in a trace, the segment selector can be useful. The next set of plot navigational tools can be used to zoom in, zoom out, or zoom to a drawn selection window. Alternatively, if you are using a mouse with a scroll wheel, the wheel can be used to zoom in and out as well, regardless of which tool is selected. Another convenient tool for navigating a plot is the pan tool, which allows you to click and drag the data or axes as desired. The home or fit all icon is useful for recentering the plot if your zoom and pan actions cause some of the data to no longer be visible. Finally, the last icon toggles whether the plot is viewed on an orthonormal scale or not. Orthonormal is a plotting convention where the visual spacing for the scales on the x and y axes are identical. By default, most data are not plotted with this convention, but a notable exception are Nyquist plots from electrochemical impedance spectroscopy data. When orthonormal is selected, notice that data can still be zoomed in and out or panned, but one axis cannot be zoomed or its scale adjusted independently of the other. There are 4 tools that are most commonly used for analyzing data in a plot. These include the peak-height, area, crosshair, and baseline tools. Applying a peak-height tool can be done by right-clicking on a trace or segment and selecting Add Tool, then Peak Height, then clicking OK. The tool has 2 pink dots that are by default tethered to the trace that are used to determine the peak height baseline. The green dot determines the peak location. Double-clicking the dialog box and then the Properties tab allows you to change how the baseline is drawn. For example, a free-sloped baseline can be selected if desired, where the pink dots are not tethered to the trace and can be moved independently. An area tool can be applied to a plot, and similarly to the unit consistency discussed earlier, AfterMath will recognize SI units when calculating area under a curve. For example, adding an area tool by right-clicking a trace of current versus time, choosing Add Tool, Area, will show units of millicoulombs, which is equivalent to seconds times milliamps. Two green dots can be moved to set the boundaries of the area being calculated, and the baseline can be adjusted using the pink dot. A crosshair tool can be added from the same right-click Add Tool submenu. The crosshair tool is simply a display of the XY values of any point on the trace, and the green dot can be moved around to show the coordinates of different locations. Alternatively, the coordinates of the current mouse location are also always shown just above the plot area. Here is the baseline tool, which shows a y equals mx plus b linear regression. Like the peak height tool, by default, the bounds of the baseline tool are tethered to the trace, and the pink dots can be dragged to any location on the trace where the baseline is desired. Slope and intercept values, along with SI consistent units, are displayed in an accompanying dialog box. I will show a couple different transforms for you now, starting with smoothing transforms. Right-click the trace and select Apply Transform, then Smoothing Transforms. There are a few different options in the menu, which represent a variety of mathematical algorithms used to smooth the data. Often, trial and error is best to determine which may be ideal for a particular set of data. The smoothed trace can either replace the existing trace or add a new trace on the plot by toggling this checkbox. Clicking OK performs the operation and shows the smoothed data. Another available transform in AfterMath is the Fast Fourier Transform, or FFT. FFT is a method used to deconvolute sinusoidal time-based data, so it can only be applied if the x-axis is in units of time. Once again, there are many different options available to the user, and trial and error can help determine the optimal combination. Clicking OK appends the FFT analysis to the plot, and either using a crosshair tool or simply zooming in on the FFT peaks can reveal the characteristic frequency of the sinusoidal waveform. The Basic tab is the default view for any experiment, and it contains the bulk of the necessary parameters. Before adding values to any parameters, there may be yellow highlighted boxes and options. These represent the parameters that must be filled in at minimum to run the experiment. One quick way to add values, if you are unsure where to start, is to use the Autofill button. This may not be the best set of parameters for every experiment, but it can be a good place to start. There is a drop-down above the tabs that shows the active instrument connected to the computer and currently selected to run the experiment. If there is no instrument connected or turned on, the drop-down will display no instrument selected. The other icons next to the drop-down allow you to audit or perform the experiment. When auditing the parameters, it runs a check of the validity of the experiment, but does not run the actual experiment. The next button is the Perform button, which runs the experiment on the actively selected potentiostat. Finally, the last button can be used to create a copy of the experiment in the archive. After the Basic tab, there is the Advanced tab, and the contents of the Advanced tab differ for every individual experiment. However, there are some common settings that appear on many experiments, such as induction and relaxation times. On the Potentiostatic Electrochemical Impedance Spectroscopy Advanced tab, for example, you can adjust the Lissajous repetition and interfrequency settling period, which may affect the duration and accuracy of the experiment. These are settings that are specific to EIS type experiments. Another example is the Advanced tab for chronopotentiometry, where you can turn on IR compensation and set an experiment end trigger. Note that an error message will appear if you try to use IR compensation with a potentiostat model that does not have that capability. An experiment end trigger can be applied to terminate the experiment if a certain condition is met. For example, if the potential is ever at or above 4 volts. Other tabs that may appear could include a Ranges tab, Filters tab, Post-Experiment Conditions tab, or a Post-Experiment Processing tab. The Ranges and Filters tabs contain settings for the potential and current ranges and the instrument filters, respectively. Post-experiment conditions can be used to help smooth transitions between experiments. For example, you can set the instrument to maintain the last potential or current applied at the end of one experiment going into the next experiment, instead of releasing or opening the cell, which occurs by default. In some situations, this may improve data quality. Finally, the Post-Experiment Processing tab contains experiment-specific options that may be useful for data analysis. Clicking the Perform button sends the experiment to the potentiostat to run. Additional experiments can also be queued up by clicking Perform again, even while the first experiment is currently running. The newly added experiments will not overwrite the current one, but rather will be added to the queue and run as soon as the current experiment has completed. An alternative to clicking the Perform button multiple times is to use a sequence, which is the first of AfterMath's advanced options I will show you. A sequence can be used to perform a number of experiments in a row, and the entire sequence itself can be performed multiple times if desired. Experiments added while a sequence is selected will be added directly to the sequence list, and then they can be dragged around in the sequence to set the execution order. The entire sequence can be run for any number of iterations, and when ready, the Perform button can be used to send the experiments list to the active potentiostat. A number of different experiments have been programmed in AfterMath for specialized types of tests, including rotator methods, dual electrode methods, spectrometer methods, corrosion methods, uncompensated resistance methods, impedance spectroscopy methods, and battery methods. For rotating methods, these are for times when using an electrode rotator in conjunction with a potentiostat. The RDE method is essentially a cyclic voltammetry experiment, but with a rotator control option built in. A sequence can be constructed to perform RDE at varying rotation rates, or alternatively, an experiment like Kucecki-Lević RDE can be used. This experiment will cycle through a number of rotation rates automatically and perform CV at each rate. If using a bipotentiostat, a dual electrode method can be used to control both the first and second working electrodes simultaneously. There are a variety of options for how each working electrode can be controlled, either potentiostatically or galvanostatically, and whether swept or maintained at a constant value. Spectroscopy and spectroelectrochemistry methods can be used when pairing a Pine Research potentiostat with a UV-Vis spectrometer. Both instruments can be controlled simultaneously to monitor the electrochemical and spectroscopic signals in concert. Corrosion techniques like linear polarization resistance, or LPR, are typically used to study the rate of corrosion of common metals like steel or brass, both with and without special preventative chemicals called corrosion inhibitors. LPR is usually performed in multiple iterations over several hours. The most common type of electrochemical impedance spectroscopy is potentiostatic EIS, where a potential sine wave is input to obtain EIS data. Alternatively, galvanostatic EIS can also be performed for systems where controlling current is preferred instead. Another specialized kind of impedance experiment is called Mott-Schottky, which is often used to determine properties of semiconductors. This method employs a narrow range of frequencies over a range of different stepped potentials, and data analysis is performed automatically by the software. Finally, special methods for battery testing called potentiostatic or galvanostatic intermittent titration, or PITT and GITT for short, can also be performed in AfterMath. PITT and GITT are ways to more gradually charge or discharge a cell while also providing an empirical calculation of the diffusion coefficient. Importing data into AfterMath and exporting data from AfterMath can be done in several different ways. Click the trace, press Ctrl and C on the keyboard, or right-click and select Copy Points. Then paste them directly into a spreadsheet in an auxiliary program such as Microsoft Excel. Be aware that this method automatically reverts all units to base SI. So for example, on this cyclic voltammogram, the units are displayed as microamps and millivolts, but when pasted into the spreadsheet, they appear as amps and volts. If you want to copy the points in the units as displayed, simply expand the plus sign on the plot to reveal the individual trace. Clicking on the trace shows the tabulated data, which can also be directly copied and pasted into a spreadsheet. This time, the values will be preserved as shown in the tabulated columns, which are units of microamps and millivolts. Multiple traces can also be selected and copy-pasted simultaneously from a plot. When pasting multiple traces, each trace will be separated by a blank row. Exporting EIS data can be done similarly to what has been described previously by copy and pasting the data from both the Bode and Nyquist plots separately. Alternatively, all 5 columns of data can be copied together by right-clicking on the data and selecting Copy Data As, then EIS 5 column. This will again paste units in base SI, and the benefit of this method is that all 5 EIS columns of frequency, Z real, minus Z imaginary, Z magnitude, and phase can be exported at once. Importing data into AfterMath can be done as simply as it can be exported. A blank plot can be created, then data directly copy and pasted from another program into the blank plot. Upon pasting, AfterMath will prompt you to select the quantity and units for the 2 columns, if there are any applicable. Importing specialized data, like EIS data, however, has its own dialog box. 3 or 5 columns of EIS data can be either imported as a CSV file or pasted directly into the dialog box, then imported at once. Bode and Nyquist plots are automatically generated once the EIS data has been successfully imported. EIS circuit fitting is an analysis tool used exclusively for EIS data. A circuit fit node can be added to a set of raw or imported EIS data, and after selecting the appropriate circuit analog, AfterMath will perform the fitting analysis. In cases where the fit is not ideal right away, manual trial and error can be performed to obtain the optimal parameters.
Hey folks, this marks the conclusion of our AfterMath crash course. One last thing to note. AfterMath offers a variety of simulation options, such as EIS circuit and transmission line simulations, as well as some DC voltammetry options, such as cyclic voltammetry simulation. Permission files might be required for certain simulations, so reach out to Pine Research Instrumentation for more information. If you have any questions, please leave a comment below or email us directly. And lastly, don't forget to like, comment, and subscribe, and we'll see you soon.